I'm not going to try to pronounce that. So thank you for doing this for me. So very quickly, mangling rules, what are they? So they came from the tool crack, and they came from the observation that dictionary were about the best things you had to crack password. They are super effective. And that if you add some way to extend your dictionary, you will be able to crack longer. So some guys called Alex Method had an excellent idea and add a language of mangling rule directly into his cracking tool. Nowadays, well, almost all the major tools have some way of mangling the wordlist rule, and also they mostly, well, those I know, they mostly still look the same, which is basically unreadable, except for HashQ, which has a very fancy language, and that's very interesting. Okay, so here is an example in case you have never seen mangling rules. So this actually comes from John the Ripper default rule set, and it is in itself a rule set, because John the Ripper has a preprocessor, and those brackets you see here and here are actually preprocessor directives, which means that this line will be extended into 12 lines, and the first one will be this line. And this means that you will project the word that comes from the word list, unless, well, when it is longer than the maximum length, when it is not at least 2 characters long, and when it is not purely alphabetic. And in case it is not projected, you will lowercase it and append 2. So that's the kind of things you do with mangling rules. So I will mostly talk about John the Ripper, so mainly because it's a tool I know the best, also because it has one of the most complete language. It has a preprocessor which I will not use here at all. It has all kind of rules you can, well, all the rules you can dream up. It even has memory modification rules that also are now in Hashcat. It has word rejection rules and rules rejection rules, flat. And all kind of things, and it's very complicated. And it's so complete that I can use it to emulate other tools' specific rules. Well, actually, it should be possible to emulate them all. So I wrote a library that is designed to parse rules from other tools and from John the Ripper and convert them to any tools. So as I wrote it for this presentation, currently it only reads Hashcat and John the Ripper. It does convert everything but bitwise shifts, ASCII increments, or Q, which I believe doubles every characters in a strange way. It's actually possible to emulate them, but it would be a very long rule. So I did not do it. So it should convert everything else, and that's important because I then benchmarked several rule sets from Hashcat, and some of the rules would not be converted. I do not believe they were very effective because, well, perhaps they were, but I do not believe they were, so I might be wrong. Okay, so how do you automatically generate a good set of mangling rules? And that is the subject here. So I chose to do that as a machine learning problem, which is I will have a training set, and I will try to train a model for it and test it against my test set. So it's the same test set in the sense it's Yahoo Contributor Network League. For training sets, I have used RoQ with and without duplicates. And for training word lists, the famous Wikipedia SRO list, and a lowercase dictionary, which is a simple list where that I clean up the list by removing all words with special characters and lowercase everything. The reason for that is that I believe that if all your words are lowercase, then your rules will be more tailored for this dictionary, and we'll see if it was a good idea. So, what is it you might do in order to take care of this problem? So you might believe that the first step is to find for each of the words in your word list, or for your training set, to find the corresponding word in the word list that is the closest. Then compute what is the shortest mutation rule between the two. Then compute how many passwords each will track, sort the rules, and good for you. Except, well, the only problem is that at each of these steps, it is either a very incomplete definition of what you want to do, or it might be too hard in a computational sense, or there might just be no correct way to do it. So here are the kind of problems that you quickly find when you sit down and start to implement some system. First of all, how to find the closest word. So that might be the easiest problem. Still, it is extremely complicated. So, for example, you might look for average time distance on Wikipedia, look how easy it is, and realize that you cannot use it at all for complex mangling rules. You can try to find the shortest mutation rules between two words, and realize that the 2 points are actually probably the same problem. Then why would you just select the closest word? As an example, let's say you have a dictionary with the word pass and the word pass 1, and you want to crack pass 1, 2, 3. Wouldn't it be more logical to select pass and say that the rule is appending 1, 2, 3? Because that's what people would do, more likely than appending 2 and 3. Why just one rule? That's a very valid question too. What do you do when several rules crack the same password? To order them. When you read that, you should think coverage problem. Also, how do you sort the rules, which is the same problem. So, in my model, someone chooses a base word in the dictionary, he mangles it, and once it is mangled, he just appends and prepares stuff. So, as an example, here is a real password from the LinkedIn link. So, somebody takes LinkedIn, he litifies it, and then he appends go and an exclamation mark. So, can somebody see what is the problem with my model here? Come on. Okay. Okay, so actually, the problem here is that if you see, do you think many people would in their head think, yeah, I will append G and 0? No, they will append go. And the problem is that certainly the user here is added go and then litified the rule. So this just to show that this model is far from perfect. Okay, I'm going to skip this because it's much too late.
You don't have to skip it that fast. I mean, if people want to go home, they can do that. But
Okay.
I'm really going to listen to the slides. Good and simple.
Okay, so in my algorithm, I start with a list of given mangling rules. So this list is actually, you put it in the tool. So you can either manually select a rule because you know they are effective. You can also steal rules from other people, which I did a lot. And you can also randomly generate them, which I didn't do alone. Then you mangle your word list with each rule. And for each word in the training set, you try to find the largest substring from the mangled word list that fits in it. So I will show you an example just after. And then from that, you know what people have appended and prepared. So you store the full rule, which will be mangling rule, append, prepared, and store somewhere that it cracks this password. Then you will be able to write the rules, and well, it will be over. Little problem, it's a bit obvious, but I didn't do it. So as I said previously, in Chapter Reaper, you can have mangling rules that reject words. Actually, the first rule I show you rejects words that are not at least 2 characters long, for example. Which means that if all of the words in your dictionary are only 1 character long, then half of the words will not be considered when cracking. Which means that if these rules crack 20 passwords, and you have another rule that considers all the words on the word list and that cracks 30 passwords, it will be actually a little less effective in terms of password cracked by password tried. So my tool right now only ranks the rules by number of password cracked, not by efficiency, but it will be corrected in the close future. So I selected that number of rules from known sets. So for example, all Johnson close rule, I took lots of rules from hashcat. The hashcat rules that are distributed with the binary. I also added exhaustive combination of simple rules, and a few combinations of rules that seem to work very well. there are still very badly performing rules in the set that need to be removed. And obviously, I didn't add any appending or prepending rule. And it's easy with this tool to steal rules that work really well in other people's sets, so you should do it. Well, this is algorithmic considerations. So my design goal here was not to be extremely fast. It was reasonably fast and fit on my workstation. So in all of this derives from a need to have this fit in 32 gigabytes of memory and to reduce the number of disk access. So this might not make a lot of sense, but it does when you take into account these limitations. So what is done is that the word list is mangled with George the Ripper for a given rule. Then for each word in the word list, I compute 2 hashes and store one of them in a binary search tree and compute 2, people in the cracking community seems to call bitmap, but which should be blue filters, for quick rejection of false positives. Then, for each clear text, I am able to find the largest substring that comes from the mangled word list that fits in that clear text. And this actually is a complicated problem because there are no good algorithm that does exactly this, or perhaps there is, but I didn't find it. So most of those algorithms are about creating some kind of huge state machine, and it's not suitable in the case where you have way more substring than you see normally used. So I'm using running hashes for matches that are at most n characters long. So there is this limitation of my approach in the sense that very long substring will not be matched. So once you have found substring, you can easily store prefixes and suffixes. So as I said, the optimization goals are no disk access and fits in my memory. And it doesn't take a knowable amount of time. So here is an example. Let's say I have as rule T0, which toggles the case of the first character, and my clear text is pass123 with the first character being capitalized. In my dictionary, I have the word pass, so by toggling the first character, I get the word pass with the first character capitalized. And the longest match becomes pass, which means that my rule T0 and append 123 does crack this password. So this is what I am storing, a list of rules, and which each rules I have the list of passwords that I crack. Once you have that, it's fairly easy. I just sort the rules by number of passwords cracked, then remove all the passwords that were cracked by this rule from the set of password cracked of the other rules, and just rerun them again, repeat, until there are no rules left. So this is a pretty approximation of the maximum coverage problem, which means that it's not a perfect solution, but should match fairly well the perfect solution for a large amount of data. So there are others that have been doing that, and for example, the best known and actually only known challenge that I know of is the best 64 challenge, which was launched in the Hashcat community, and the challenge was about, you had the PHPBB leak, and you had to find a set of word lists to apply to a word list that is called top 10K, and you had to crack as much password as possible. So, when the contest started, I already had all that ready for since 6 months. So I was like, I'm going to be really good at this contest. So I just ran my script, went to bed, and the following morning, I realized that if I had played, I would only have been 7th, which totally sucked for somebody who had all the tooling ready for months compared to other people that did off-the-shelf solution in just 2 days. So, it was actually fairly cool because thanks to that contest, I found a ton of bugs and a ton of rules that were missing from my list. And I list won. So what it did was pretty similar to what is described here, except it did not do appending and prepending discovery, which means that it just had the rule already backed with append and prepend. That we had a lot of rules that were automatically generated, that I suppose this solution would not have scaled because of the choice of technology, yet it was extremely pertinent given that, well, it was made basically a few hours, and that it won. And also, he had many early rules. For example, these rules appends 2, appends 4, and then removes the last 2 characters. And it doesn't do anything at all. So maybe the last step was exactly the same as what I did, which is the step where you rank the rules. So for the benchmarks, I have 3 sets of rules, which have been trained with different training sets and word lists. So, well, basically you have those 3 sets. One of you is computed with having Roku as a set of passwords and Wikipedia Travel as a word list. The second has Roku with unique passwords, and the third is with unique password for Roku and the cleaned up word list. I also have added all the following rules, which are John the Ripper default jumbo rules, hashcat best 64, hashcat something that's called generated, dead one, and the best 80 that were provided by Eric's lead. So here are the results by using Roku as a word list against the Yahoo leak. So what can be observed here is that, first of all, my rules are totally lit, but they're really good. Best 64 is the next best rule. It performed extremely well, but it's way too short. Other rules have something that is very typical of handmade rules, which is that they, hashcat 64 has that too. They start really strong and they hit a peak, and then the performance is much worse. And you have this effect just here for hashcat 64. So, on the other hand, generated rules, even this one, this one is a generated rule, and you can see that it still yields some passwords, even with a high number of rules, which kind of shows that it's actually much better to trust a computer to do your sorting than to do it yourself. Also, using your Roku as a word list, it's the same thing but zoomed, so that you can much better see what is happening. And that, well, it's interesting to see that hashcat, as far as I know, it's being revised in the sense that rules from the contest have been added, and there has been some kind of automatic system to put them, but it's basically handmade in the sense that everything was edited. And it's still extremely effective. And it's in stark contrast to other rule sets that performs fairly badly. And what is also interesting is that when you use Wikipedia as a word list, it's not the same set of word lists that wins. Yet, my tools generate word lists that are significantly better than other tools. So that is the conclusion. It works fairly well. So you just have to download it and you can try it. You can add your own rules, and I would be very interested in pull requests that have excellent rules. It's actually kind of hard to use. Many people have tried it, and I had to help them a lot on IRC because I'm not very good at documenting. It's not entirely obvious how this works. It's all kind of C files that interact with each other, and there's a big make file that does all kind of things. It also has benchmarking scripts that have been used to create this presentation. And the only thing you have to look at is if you run it on a computer that doesn't have 32 gigabytes of memory, then you will swap very quickly and you will be in a world of misery. So beware, look out for memory usage. There are still a lot of optimizations that can be done. For example, it's obvious that the best rule is the identity rule. So you can just pre-apply it, remove all passwords that are cracked by the identity rule, and start from that. And you will reduce a lot the runtime performance and memory usage. Also, what would be nice is to add better rules, obviously, and to rank them by effectiveness and not by password crack. Finally, well, against public leaks, it seems that John the Ripper default rules need an overhaul. And also, Hashcat base 64 is performed extremely well, but there are only 64 rules, and they need more. So that's it. You have bonus, that's the kind of things that are generated. So it looks pretty strange, but it's actually incredibly effective. And actually, you will recognize rules that are in other sets, but in the same way. And, well, there are still things to do, so, well, this is a bonus part of the presentation. There are still things to do if you want to use the rule. You have to clean them up a bit, actually, today. So, in the future, this will be handled by the other library I'll talk about, which can also be downloaded at the same place, which is able to optimize rules, well, a little bit, and well, it should be awesome. Questions? Yeah, it was very great, right?